Okay, hello everybody. So we continue our discussion on surface plasmon polaritons, and as discussed earlier, these are generated at the interface of a dielectric and conductor when you have an electromagnetic wave incident in the plane of the interface. Now, in our case, we have considered propagation of the wave in the direction x, and so we will have evanescent waves. So z becomes the perpendicular. So this will be our z axis. X will be in this direction and y in the orthogonal direction. So the interfacial plane is defined by the xy plane, and z defines the perpendicular direction to the interface. So in such a situation where you have an electromagnetic wave propagating confined to this interface, we will have evanescent waves fields getting into the media along the z, and these will be exponentially decaying function, where we have defined it as minus kdz in the dielectric and the decay constant of kc in the conducting side. So how do we define the electric field? We define it by an amplitude Ez and a propagating part which is exponential I kx minus omega t. So this kx, this one is the propagation vector, and because it's along x, it is written as kx. Now something to note is that the amplitude is a function of z, and this arises from the evanescent fields that we have discussed just a moment earlier, where in the z greater than 0, the positive z region, which is basically the dielectric region, you have it's an exponentially decaying function with a decay constant kd, while in the conductor region, where z is negative, it is defined as exponential kcz. Z being negative, it will give an exponentially decaying form. Now, with this in mind, let's get into the Maxwell's equations. So, to reach the wave equations, we eliminate all the h. So, we get an equation only in electric field, and here exactly that's what we have done. So, curl of curly is given by minus mu naught del square d del t square, d being the displacement vector, and the d can be written as epsilon, which is the dielectric constant, epsilon naught the free space permittivity multiplied by electric field. Now, once we substitute this in this equation, we have minus mu naught epsilon naught epsilon del square E del t square. And from time derivative, we know from the form of the electric field that we have used, the time derivative will show up in this omega. So what we have is 1 by mu naught by epsilon naught can be substituted by 1 by c square. We have an epsilon left, and the time derivative gives you I omega square E. And from here, left hand side, however, this curl of curly becomes minus del square E, and on the right, if you see, we will have epsilon omega square by c square E, which boils down to the wave equation. The way we will write it is this. So omega square by c square can be replaced by k0 square, k0 being the free space propagation vector given by frequency by velocity c. So k0 epsilon E. So this equation, as we have it, is called the Helmholtz equation. So we'll go a little further again in this. So what we'll do is we will, we have the form of electric field. So as we have already done, all the time dependence has been taken care of by already doing the partial derivative with respect to time. So what we will do is this E that we have mentioned in this relation, we will substitute by E the spatial part of it, which is nothing but your the Ez that we talked of, exponential I kxx, and the Laplacian, the del square E, is given by double derivative with respect to x And please note that we don't have an y dependence, that is what we have told in the first place. So the derivative with respect to y goes to 0 and we are left with only the x and z components. Now with this in mind and knowing the form of the electric field, we have this derivative with respect to x comes out to be ikx square E, and z of course will come out to be either the kd or the either kd square E for the dielectric or kc square E for the conductor. So once we have all these, what we can write in a more general form, if we had not done this derivative, then it would have turned out to be, we still keep the z, so we have just removed we have substituted the derivative with respect to x by ikx rather, and then this becomes 0. Okay, so we just can go one step further in this. So what we do is, because we know the dependence of z, so in for z greater than 0, that is in the dielectric, we have kd square instead of this, because as you see here we had this derivative here, we had it as kd square plus k0 square epsilon minus kx square. This should go to 0, and for z less than 0 we have kc square plus k0 square epsilon minus kx square. This should go to 0. Okay, so these relations we will need again later on, so please remember them, and this is where I'll stop today's lecture. Thank you.